Attempt number one. All I really did was get a new battery. It's just a sealed lead acid battery, but I mean, you know, infinite current. I guess I'm just gonna pray that it doesn't explode. Oh, look at that! I think it works. Okay, so this should get red hot in like a moment. Yep. Not quite heating up as fast as I would have expected. Is this warm? Ooh! In case that wasn't made obvious by the sound of sizzling, yes, it does get hot. Enough to discolor the paperclip I was using. I think I could make a tighter coil. That would probably help a lot, and I'll probably do that next. Quick sizzle check. Yes, I've made a new coil. This new one is 10 turns. This old one was 7. Way more consistent in shape, and also probably roughly half the diameter. I'm thinking this should be way better now. So let's see how long it takes the paperclip to get visibly hot. There we go. Oh, smoke. And it is red hot. So that was about 30 seconds or so. I've made some upgrades. The main one being two 12-volt batteries, lead acid batteries. And they allow for much stronger current. So I have a demonstration to show how much current this draws and sort of get behind the properties of induction heating. What I've done is I've wired up my multimeter in series with the power supply so that I can measure the current flow. And as you can see, when there's no load in the work coil, I am plugging it in now, it idles around 2.5 amps. That'll settle down once it heats up and gets really up to speed. Plugged it in, you can see the oscillations on the oscilloscope, but let's get to the actual demonstration. What I have is a very thin gauge copper wire, a thicker gauge, well, steel wire, really it's a paper clip, but I mean it's made of steel, an even thicker gauge copper wire, and, well, a screwdriver. So, inductive heating, the way it works is through eddy currents
and magnetic hysteresis. Now, magnetic hysteresis is only possible in ferrous materials because, well, they're the only materials that can have magnetic domains or dipoles, whatever you want to call them, inside them. Eddy currents can work in any material. That's why heating technically works in copper. It's just much slower and captures much less of the energy and by proxy draws much less current. Magnetic hysteresis generates heat because in a rapidly changing magnetic field, the magnetic domains inside a ferrous material are forced to flip back and forth rapidly in sync with the magnetic field, and they naturally resist change, so this flipping back and forth generates heat inside the metal. Eddy currents generate heat as, well, a current manifested inside a metal, which naturally has a resistance, will generate heat just by proxy of all materials are naturally lossy in that way.
In a ferrous material, such as this paper clip, on a matter of 10 seconds, it is now red hot. Put it back in, gets even hotter. If we get a thinner gauge, copper wire, I know it doesn't look like copper, but you have to trust me, it's copper on the inside, it's just tin on the outside. You will see that even though it is thinner and realistically should heat up faster since it is thinner, it doesn't. It also doesn't draw a load on the multimeter. So bigger copper wire. It, yeah, takes a little. That's again because the copper wire itself is non-ferrous. But if we get a screwdriver, a much thicker ferrous material, and put it in the work coil, as you can see, the draw jumps a little bit. That is because, I mean, very simply, it's a ferrous material and it's going to be heating up quite fast. And lo and behold, you get that nice, beautiful red glow of a scorching hot material that I have burned my fingers on a couple more times than I'd like. Let's see if it sizzles. I've now disconnected the circuit, and I will be going into details on how this circuit actually works.
Here's the schematic I use for my induction heater. So when the battery is plugged in, since no resistor is perfect, then the current will reach one of the MOSFETs first at random, turning, say, this top one on. And when it's on, that brings this gate to be a ground. That makes this whole line a ground. And what that means is that this fast out will short the gate of this MOSFET back to ground, making sure it can't turn on. And when this top MOSFET is on, it allows current to flow through one of the inductors, through the work coil, and into the resonant circuit capacitor bank, then to ground. Since this resonant circuit, it'll start resonating or oscillating between positive and negative. It starts positive, but it soon goes to negative potential at this point. And having the negative potential here will ground the gate of this MOSFET, effectively shutting it off. And when that MOSFET is off and this fast diode isn't working, then current will have to flow through the battery, through the bottom resistor, into the bottom MOSFETs. That will turn it on, and from there, the cycle repeats as we're back at the same situation where this MOSFET turned on, giving the rapidly alternating strong voltage current through the work coil.